Most men see only what they expect to see, and this blindness costs them the truth. I have spent decades watching birds, sketching their wings, studying their movements. Every morning in Milan, I would climb to my workshop's highest window and observe the swallows as they cut through the dawn air. People believe flight comes from flapping. They see a bird beat its wings and assume the beating lifts the creature skyward. This assumption seems logical. After all, we move our arms to swim, we move our legs to walk. But they are wrong. The secret is not in the flapping, it is in the shape, the curve of the wing, the way air flows over and under it, the invisible forces that form when wind meets a properly designed surface. I discovered this by accident, watching a leaf fall in a peculiar spiral. That moment changed everything I thought I knew about the sky. Before we continue, take a moment to notice where you're listening from. And if this story stays with you, you're welcome to return tomorrow for what comes next. My fascination with flight began in childhood, long before I understood what I was truly seeking. I was perhaps 7 years old when I first made a kite from scraps of linen I found in my grandfather's workshop in Vinci. The cloth was coarse and yellowed, but when I stretched it between two olive branches and tied it with hemp cord, something magical happened. The wind caught it, pulled it skyward, and for a brief moment I held the sky itself in my hands. My father, Ser Piero, found this pursuit foolish. He was a notary, a man of documents and practical affairs. When he discovered me in the courtyard, lying on my back with my contraption dancing overhead, he shook his head with that particular disappointment reserved for sons who refuse to follow sensible paths. "Leonardo," he said, "the birds fly because God wills it. Men have their own purposes." But even then I knew he was wrong. Not about God's will, but about the separation he drew between the flight of birds and the purposes of men. I could feel the pull of the wind against my kite, the way it responded to subtle changes in angle and tension. This was not divine mystery. This was mechanism, waiting to be understood. The hills around Vinci offered perfect vantage points for observation. I would climb the slopes above our house before dawn when the air was still and the hunting birds began their morning flights. I watched kestrels hover motionless against the wind, their wings barely moving, and I wondered how they achieved such perfect stillness, while the wind that pulled my kite so fiercely seemed not to disturb them at all. The larger birds fascinated me most. Eagles and hawks possessed a majesty that smaller birds lacked, but more than that, they revealed secrets that sparrows and finches concealed through their rapid, chaotic movements. When a hawk soared, I could see the precise angle of its wings, the way its feathers adjusted to catch and redirect the flowing air. These great birds seemed to understand something fundamental that escaped human comprehension. I began making detailed drawings, though my early attempts were crude. I had no formal training in anatomy or proportion, only an insatiable need to capture what I observed. I drew wings from every angle I could manage, trying to understand their structure. What I noticed troubled me. The drawings never matched what I saw in flight. On paper, wings appeared as simple appendages like arms or legs. In the sky, they became something altogether different, instruments of incredible sophistication that transformed air itself into solid support. My breakthrough came through careful observation of wing beating patterns. Most people, watching a bird fly, see only the obvious up and down motion. But if you watch closely, really closely, you notice something else. The wings don't simply beat up and down like a man flailing his arms. They follow complex paths, twisting and adjusting continuously. The feathers separate and realign, creating surfaces that change shape dozens of times with each beat. More puzzling still, I observed that many birds barely flapped at all during their most impressive flights. I once watched a vulture circle the valley for an entire morning without moving its wings more than a few times. It rose steadily higher, riding invisible currents, gaining altitude through some mechanism I could not fathom. If flight came from flapping, how did this bird climb skyward while essentially motionless? This contradiction led me to an important realization. People focus on the flapping because it's visible, dramatic, obvious, but the vulture's motionless ascent suggested that flapping might be only one part of flight, perhaps not even the most important part. The bird was clearly using the air itself as a support, the way a boat uses water, but air, unlike water, was invisible. How could something invisible provide such solid support? When I was apprenticed to Andrea del Verrocchio in Florence, I found my first real encouragement for these investigations. Verrocchio was a man who understood that art and science were not separate pursuits, but different aspects of the same search for truth. In his workshop, surrounded by painters, sculptors, and engineers, I learned that my obsession with flight was not foolishness but legitimate inquiry. The eye, which is called the window of the soul, Verrocchio told me one afternoon as I sketched yet another bird wing, is the principal means by which understanding may most fully appreciate the infinite works of nature. He encouraged me to trust my observations over received wisdom. If the book said birds flew through divine intervention while my eyes showed me mechanical principles at work, I should follow my eyes. This permission transformed my approach entirely. I stopped trying to reconcile what I saw with what I had been taught and began simply recording as precisely as possible exactly what occurred. I established a routine of systematic observation. Each morning, before the workshop began its daily activities, I would position myself at the highest window and watch the birds for exactly 1 hour. I noted the weather conditions, the direction and strength of the wind, the types of birds active, and their specific behaviors. I developed a shorthand notation system to record wing positions, flight paths, and the relationship between visible wing movements and actual motion through the air. These sessions revealed patterns I had not noticed during casual observation. Birds adjusted their flight techniques based on wind conditions. In still air, they flapped almost continuously. In moderate wind, they combined flapping with periods of gliding. In strong wind, many species barely flapped at all, instead manipulating their wing shapes to harvest energy from the moving air itself. The most significant pattern was this: successful flight always involved the bird working with the air rather than fighting against it. Birds seem to understand air as a medium with its own properties and behaviors. They read these properties instinctively and adjusted their techniques accordingly. This suggested that human flight would require similar understanding, not just mimicking the physical motions of birds, but comprehending the underlying principles they employed. By my 20th year, I had filled 3 notebooks with observations and sketches. Each page brought me closer to understanding that flight was not about conquering the air through brute force, but about collaboration with invisible forces that followed discoverable rules. The birds were my teachers, but they taught through demonstration rather than explanation. My task was to decode their lessons and translate them into human understanding. The linen kite of my childhood had become something far more significant. It was my first glimpse of the truth that would occupy me for the rest of my life, that the boundary between earth and sky was not as absolute as men believe, and that understanding could bridge even the gap between the walking and the flying. When I arrived in Milan to serve Duke Ludovico Sforza, I gained access to something that transformed my understanding entirely: the Duke's magnificent library. Among the collected works of ancient and contemporary scholars, I found treatises on anatomy that opened new paths of inquiry. But it was not the books that provided my greatest breakthrough. It was a dead crow I found one winter morning in the castle courtyard. The bird had died during the night, likely from cold or injury. Most men would have seen only carrion, something to be swept away and forgotten. I saw opportunity. Here was a chance to examine the mystery of flight from within, to understand not just what birds did, but how their very construction made flight possible. I brought the crow to my workshop and began what would become my first serious anatomical investigation. Using the finest blade I possessed, I carefully separated skin from muscle, muscle from bone, revealing layer by layer the hidden architecture of flight. What I discovered astonished me so completely that I questioned everything I thought I knew about the nature of birds. The bones were hollow, not partially hollow as I might have expected, but extensively hollow throughout their structure. When I held a wing bone up to the light, I could see through it in places. The bone walls were incredibly thin, yet when I tested their strength, they proved remarkably resistant to bending and breaking. This was engineering of the highest order, a solution to the fundamental problem of flight that I had not even recognized existed. Weight. Everything about successful flight, I realized, came down to weight. I had been so focused on the mechanics of wing movement that I had never properly considered the challenge of lifting weight into the air. Now, examining the crow's hollow bones, the revelation struck me with perfect clarity. Every ounce mattered. Every unnecessary gram was the enemy of flight. The bird's entire skeleton had evolved to provide maximum structural strength with minimum mass, but the bones were only the beginning. As I continued my dissection, I found that the bird's entire body reflected the same principle. The muscles were precisely calibrated, developed only where needed for flight, with no excess mass anywhere. Even the internal organs seemed arranged for optimal weight distribution and aerodynamic efficiency. Most remarkable of all were the feathers themselves. I had always seen feathers as simple coverings, like fur on a mammal or scales on a fish. Under careful examination, they revealed themselves as instruments of extraordinary sophistication. Each feather consisted of a central shaft supporting hundreds of smaller branches, which in turn supported thousands of even smaller filaments. These filaments interlocked through tiny hooks, creating surfaces that could be rigid when needed for support, flexible when needed for maneuverability. The primary flight feathers displayed the most elegant engineering. They were asymmetrical, with the leading edge narrower and stiffer than the trailing edge. This asymmetry, I realized, must serve a specific aerodynamic function, though I did not yet understand what that function might be. The feathers could separate to allow airflow through the wing during certain parts of the flight cycle, then close to create solid surfaces when maximum lift was required. I preserved the most perfect wing in wax, maintaining it exactly as I found it during dissection. This specimen became my reference point for all subsequent investigations. Whenever I observed living birds and wondered about the mechanics of their flight, I could return to this preserved wing and examine the precise arrangement of feathers, the articulation of joints, the attachment points of muscles. The preserved wing revealed something that observation of living birds had obscured. Flight was not a single action, but a complex orchestration of many small actions working in perfect coordination. Each feather could be independently controlled. Each joint could adjust its angle with remarkable precision. The wing was not a simple paddle pushing against air, but a sophisticated instrument capable of creating many different shapes and surfaces as needed. This anatomical knowledge forced me to reconsider everything I had observed about bird flight. When I watched hawks soaring without visible wing movement, I now understood that their wings were actually making constant, minute adjustments. Feathers were shifting, joints were flexing, surfaces were continuously reshaping themselves in response to changing air conditions. What appeared as motionless soaring was actually intensely active flight, with the bird making hundreds of tiny corrections every minute. The comparison with human anatomy was sobering. I calculated the wing area required to lift a man of average weight. Even using the most efficient proportions I could derive from bird anatomy, the wings would need to span more than 30 feet. The muscle development required to power such wings would add enormous weight, demanding even larger wings, creating a cycle that seemed impossible to resolve. More troubling still was the fundamental difference in skeletal structure. Human bones were solid, heavy, designed for walking and manipulation rather than flight. Our muscle distribution was entirely wrong for aerial locomotion. Our body proportions made us creatures of the ground, not the sky. Yet the anatomical investigation yielded one crucial insight that would guide all my future work. The crow's body was a perfect example of form following function. Every element of its construction served the requirements of flight. Nothing was arbitrary, nothing was decorative, nothing was wasted. If humans were to achieve flight, we would need to apply the same principle. We could not simply strap wings onto human bodies and expect success. We would need to create flying machines that embodied the same efficiency, the same perfect marriage of lightness and strength that I found in the crow's anatomy. The preserved wing became my teacher in ways that living birds could not. It showed me that flight was not about overpowering air through brute force, but about understanding air as a medium with specific properties that could be exploited through intelligent design. The bird's wing was not just a propeller or a paddle, it was a sophisticated airfoil, shaped and controlled to interact with air in ways that created the forces necessary for sustained flight. This anatomical knowledge also revealed why my childhood observations had been both accurate and incomplete. I had correctly noticed that successful flight involved working with air rather than fighting against it. but I had not understood that this cooperation required precise engineering solutions. The bird's anatomy was the hardware that made collaboration with air possible. As I carefully wrapped the preserved wing and placed it in my collection of study specimens, I felt both humbled and encouraged. Humbled by the complexity I had discovered, the elegance of solutions that made my crude mechanical attempts seem childish, but encouraged because complexity was not mystery. What could be understood through careful study could eventually be reproduced through intelligent design. The dead crow had taught me more about flight in one afternoon than years of observation had revealed. It had shown me that the secret lay not just in watching what birds did, but in understanding how they were constructed to do it. The anatomical discoveries had shown me how birds were constructed for flight, but they raised an even more fundamental question: what exactly was air, and how did wings interact with it to create the forces that kept birds aloft? This question consumed me for months after my dissection of the crow. I knew that understanding the bird was only half the puzzle. I needed to understand the medium through which it moved. Most people in my time considered air to be nothing, an absence rather than a substance. The space between objects was simply empty, waiting to be filled. But my observations of flight had convinced me otherwise. Birds clearly pushed against something solid enough to support their weight. Air had to possess properties, behaviors, measurable characteristics that could be studied and understood. My first breakthrough came through a simple experiment. I dropped objects of identical weight, but different shapes from my workshop window. A flat wooden disc fell slowly, rocking back and forth as it descended. A wooden ball of the same weight fell straight down much faster. The difference had to be air resistance, but this suggested that air was not uniform nothingness. It responded differently to different shapes, creating more resistance against some surfaces than others. This observation led me to construct what became my most important experimental apparatus, a glass sphere filled with colored smoke. I sealed aromatic herbs inside the sphere and heated it gently, creating visible currents within the contained air. For the first time, I could actually see air movement. What I witnessed revolutionized my understanding completely. The smoke moved in patterns, swirls, currents, streams that followed predictable paths around obstacles. When I moved objects through the sphere, the smoke revealed how air flowed around them, creating areas of turbulence behind some shapes while flowing smoothly around others. Air behaved exactly like water, following the same principles of flow and resistance that I had observed in rivers and streams. This revelation struck me with tremendous force. If air flowed like water, then the principles that govern boats and ships might also apply to flight. A boat's hull was shaped to move efficiently through water, minimizing resistance while providing stability and control. Could a bird's wing be understood as a hull designed to move efficiently through air? I began testing this hypothesis with careful observations of water flow. I built small wooden models of different shapes and observed how water moved around them in a clear stream. Sharp-edged shapes created turbulent wakes, with swirling, chaotic water behind them. Smooth, curved shapes allowed water to flow cleanly along their surfaces, reuniting gently downstream with minimal turbulence. The implications for flight were immediate and profound. Wings that created turbulent air behind them would waste energy and create drag. Wings that allowed air to flow smoothly would move through the sky with maximum efficiency. This explained why bird wings had their particular curves and tapers. They were designed to manage airflow, not just push against air. But there was more. My glass sphere experiments revealed that air had weight and substance. When I heated the sphere, the smoke rose predictably, but when I cooled it, the smoke sank. Air of different temperatures had different densities, different weights. This meant that birds might use these variations to their advantage, riding currents of rising warm air to gain altitude without effort. I tested this theory by observing birds on different types of days. On hot afternoons, when the sun heated the ground unevenly, large birds soared effortlessly in tight circles, barely moving their wings as they climbed steadily higher. They were riding columns of rising warm air, using the sun's heat as their engine. On cool, overcast days, the same birds flapped continuously and struggled to gain altitude. This discovery explained the mystery of soaring flight that had puzzled me since childhood. Birds were not defying gravity or achieving flight through pure wing power. They were reading the invisible landscape of the air itself, finding and using currents and thermals the way a sailor uses favorable winds. The more I studied air movement, the more I realized that the atmosphere was not empty space, but a complex, three-dimensional ocean with its own weather, currents, and behaviors. Mountains created updrafts on their windward sides and downdrafts on their leeward sides. Valleys channeled airflow like riverbeds channeled water. Even buildings and trees created predictable patterns of air movement that skilled birds could exploit. I began mapping these invisible air currents around Milan. Standing on high towers and rooftops, I released small feathers and watched their paths, noting how air moved around obstacles and through openings. I discovered that birds knew this invisible topography intimately. They had favorite soaring spots where reliable updrafts could be found, preferred routes that took advantage of helpful air currents, and careful avoidance of areas where dangerous turbulence made flight difficult. This knowledge transformed my understanding of what flight actually required. It was not enough to simply copy the mechanical movements of wings. Successful flight required reading and using the medium itself. A bird was not just a flying machine but also a pilot, constantly adjusting its flight path based on real-time assessment of air conditions. The glass sphere also revealed something else crucial about air movement. When air flowed over curved surfaces, it behaved differently on the top and bottom. Air flowing over the curved upper surface of my test objects moved faster than air flowing beneath them. I did not yet understand why this created lifting force, but I could observe its effects. Curved shapes placed in moving air experienced an upward push that flat shapes did not. This observation connected directly to my anatomical studies of bird wings. Every wing I had examined was curved on top and flatter on the bottom. This asymmetric shape was not accidental, but essential to creating the forces that supported the bird in flight. The wing's curve was working with airflow patterns to generate lift, not just through downward wing beats, but through the continuous passage of air over and under the wing surface. I began to understand that flapping was only one of several mechanisms birds used to stay aloft. The curved wing shape created lift whenever air moved across it, whether from wing beats or from the bird's forward motion through the air. This explained how birds could glide long distances without flapping. Their curved wings continued generating lift as long as they maintained forward speed through the air. The glass sphere experiments taught me that air was not the enemy of flight, but its essential partner. Birds did not conquer air through brute force, but collaborated with it through intelligent design and skilled piloting. This partnership between wing shape and airflow was the true secret of flight, the mechanism that I had been seeking since childhood. Understanding air as a substantial medium with discoverable properties gave me hope that human flight was possible. If air followed consistent laws, if these laws could be studied and understood, then machines could be designed to work with air just as birds did. The challenge was not to overcome air, but to understand it so thoroughly that we could design wings worthy of its partnership. The morning that changed everything began like countless others. I was in my workshop in Milan, grinding pigments for a commission, when an autumn wind rattled the shutters and drew my attention to the courtyard below. A sycamore tree near the castle wall was shedding its seeds, and dozens of them spun through the air like tiny dancers, each one rotating as it fell. I had seen such seeds before, of course. Every autumn brought the same display, but on this particular morning, something made me pause and truly observe what was happening. One seed caught my eye. It fell differently than the others. Instead of the usual chaotic tumbling, this seed maintained perfect stability, spinning with mechanical precision as it descended. More remarkably, it was falling much slower than a simple drop should allow. I set down my work and moved to the window for a better view. The seed continued its controlled descent, spinning steadily, and I realized I was witnessing something extraordinary. The seed was not simply falling under the pull of gravity, it was flying. This revelation struck me with such force that I immediately abandoned my morning tasks and rushed downstairs to collect fallen seeds from beneath the tree. In my hands, these small natural objects felt different than they had before. They were not just seeds dispersed by wind, they were perfectly designed flying machines. Back in my workshop, I examined the seeds under the strongest magnifying glass I possessed. What I discovered amazed me. Each seed consisted of a central body containing the future plant, attached to a thin, flat wing that curved slightly along its length. The wing was asymmetrical, thicker at the leading edge where it attached to the seed, tapering to a thin trailing edge. When I held the seed up and spun it between my fingers, it immediately sought a stable rotation, the wing cutting through air with remarkable efficiency. I began systematic experiments immediately. I climbed to the highest accessible point in the castle and released seeds one by one, timing their descent and observing their behavior. Every seed spun as it fell, but the rate of spin and the speed of descent varied based on the seed's condition and the air currents it encountered. Damaged seeds tumbled chaotically and fell quickly. Perfect seeds maintained steady rotation and descended slowly, traveling considerable horizontal distances as they fell. The mechanism became clear through careful observation. The spinning wing was creating an upward force that partially opposed gravity. This was not the lift I had observed in bird wings, which required forward motion through air. This was something different, a rotational lift that worked even when the seed was moving primarily downward. I tested this hypothesis by creating artificial seeds from wood and cloth. My first attempts failed completely. They tumbled without control and crashed to the ground. But as I refined the proportions, matching more precisely the dimensions and weight distribution of natural seeds, my artificial versions began to work. They spun as they fell, descended slowly, and traveled significant distances from their release point. The breakthrough came when I realized that the seed's wing was not simply rotating through air, it was creating its own wind. As the wing spun, it pushed air downward, and by Newton's principle of equal and opposite forces, the air pushed back upward on the wing. The faster the spin, the greater this upward force became. But there was more to discover. I noticed that natural seeds did not spin at random speeds. They quickly settled into a specific rotation rate that remained remarkably constant throughout their descent. This suggested that each seed found its optimal spinning speed automatically, balancing the upward force from rotation against the downward pull of gravity. This automatic stability fascinated me. The seed required no pilot, no conscious control. Its design inherently found and maintained the correct flight characteristics. This was engineering of the highest order, a flying machine that flew itself. I began collecting seeds from different trees, comparing their designs and flight characteristics. Maple seeds were larger and spun more slowly than sycamore seeds. Ash seeds had different wing shapes that produced different flight patterns. Each species had evolved its own solution to the challenge of controlled flight, but all relied on the same basic principle of rotational lift. The implications for human flight were profound but complex. The seed's rotating wing created lift without requiring forward motion, but it also created no horizontal control. Seeds could not choose their direction or destination, they went where the wind took them. For human flight, this was both inspiration and limitation. I began designing machines based on the seed principle. My first models were simple rotating wings mounted on vertical shafts. When I spun them by hand and released them, they rose briefly into the air before falling back down. The rotational lift was real and measurable, but my human-powered versions could not sustain the high rotation speeds that effective lift required. Still, these experiments proved that lift could be created through rotation alone. These suggested possibilities for human flight that did not depend on flapping wings or forward motion. Perhaps a large enough rotating wing, powered by human effort or some mechanical device, could lift a man into the air. But the seed taught me something even more important than rotational lift. It demonstrated that flight was not about overpowering natural forces, but about finding ways to work with them elegantly. The seed did not fight gravity, it used rotation to partially neutralize gravity's effects while accepting a controlled descent. It did not fight air resistance, it used air resistance as the medium through which its rotation created lift. This principle of elegant collaboration with natural forces became central to all my subsequent thinking about flight. The most successful flying machines, I realized, would be those that found ways to partner with gravity, air resistance, and wind, rather than simply opposing them through brute force. The sycamore seed also revealed the importance of automatic stability in flight design. Birds achieve stability through constant conscious control, making hundreds of tiny adjustments every minute. But the seed achieves stability through intelligent design alone. Its shape and weight distribution naturally maintain proper flight characteristics without any control inputs. For human flight machines, this suggested that built-in stability might be more practical than requiring human pilots to maintain control through continuous conscious effort. A well-designed machine should want to fly properly, just as the seed wanted to spin at its optimal rate. I preserved several perfect sycamore seeds in my collection of flight specimens. Whenever my more complex mechanical designs failed or behaved unpredictably, I would return to these simple natural machines for inspiration. They reminded me that effective flight was not necessarily complicated flight. The seed achieved controlled descent through one simple mechanism, a curved wing spinning at the right speed. Years later, when I had developed more sophisticated understanding of lift and airflow, I returned to the sycamore seed with deeper appreciation for its elegance. The spinning wing was creating the same low-pressure zone above its curved surface that I had discovered in bird wings, but it was doing so through rotation rather than forward motion. The seed had taught me my first lesson in the fundamental physics of lift, though I did not yet have the knowledge to understand it fully. That autumn morning when I first truly saw the falling seed changed my approach to flight forever. It taught me that nature's solutions were not always obvious, that careful observation could reveal mechanisms hidden in plain sight, and that the most elegant flying machines were those that worked with natural forces rather than against them. The tiny spinning wing of a sycamore seed had shown me that flight was not about conquest but about collaboration. Armed with my new understanding of airflow and rotational lift, I began the most intensive period of practical experimentation in my career. The sycamore seed had shown me that flight was achievable through intelligent design, but translating that knowledge into human-scale flying machines required countless hours of building, testing, and refining. I established a workshop routine that consumed my mornings entirely. The wings featured a pronounced curve on the upper surface, tapering to thin trailing edges just like bird wings. The proportions matched those I had calculated from measuring various birds, scaled appropriately for the model's size and weight. This model, carved from seasoned linden wood and fitted with cloth-covered wings, became my masterpiece of small-scale flight. Released from the tower, it would glide smoothly across the courtyard, covering distances of more than 100 feet while losing altitude gradually and controllably. More importantly, it flew with inherent stability. When disturbed by air currents, it would automatically return to stable flight without tumbling or spinning out of control. The success of this gliding model proved conclusively that the principles I had discovered were correct. Lift could be created through wing shape alone, without flapping or rotation, as long as the wing moved through air at sufficient speed. The curved upper surface caused air to move faster above the wing than below it, creating the pressure differential that generated upward force. But this success also highlighted the fundamental challenge of human flight. My best gliding model weighed less than a pound and had a wingspan of nearly 4 feet. Scaling up to lift a human being would require a machine with wingspan approaching 30 feet and structural weight that seemed prohibitive given available materials. I attempted to solve this scaling problem through mechanical advantage. If human muscle power was insufficient to sustain flapping flight, perhaps it could be stored and released in controlled bursts. I designed spring-loaded mechanisms that could be wound up like clockwork and then released to power rapid wing beats. These devices worked in principle but proved too heavy and complex for practical flight. The power-to-weight problem led me away from flapping mechanisms toward pure gliding flight. If a human pilot could launch from sufficient altitude, perhaps a well-designed gliding machine could provide sustained flight without requiring continuous power input. This approach would depend on the pilot's skill in reading air currents and finding thermals, just as soaring birds did. I began designing full-scale gliding machines based on my successful small models. These designs featured lightweight wooden frames covered with cloth or thin leather, with the pilot lying prone beneath the wings to minimize drag and provide optimal weight distribution. The pilot would control the machine through shifts in body weight and manipulation of small control surfaces, much as I had observed birds adjusting their flight through subtle changes in wing and tail position. My most advanced design incorporated everything I had learned about flight stability and control. The wings featured the optimal curve I had discovered through testing, with a slight upward angle that provided inherent stability. Small movable surfaces at the rear allowed the pilot to control direction and pitch. The entire structure was designed to be as light as possible while maintaining adequate strength for human flight. I constructed a full-scale prototype of this design in my workshop, though I never attempted to test it with a human pilot. The machine was beautiful in its simplicity, elegant lines that captured the essential elements of bird flight while accommodating human limitations. The wings spanned 28 feet, providing sufficient area to support the man of average weight at reasonable gliding speeds. Testing this machine required a different approach than my small models. I loaded it with sandbags approximating human weight and launched it from the highest point available to me. The results were encouraging but limited by my testing conditions. The machine glided successfully, maintaining stable flight for the duration of its descent, but I could not test its performance in rising air currents or evaluate the effectiveness of its control systems. The wooden flying model that achieved my greatest success became my most prized possession and the centerpiece of my flight studies. Whenever visitors questioned the possibility of human flight, I would demonstrate this model's capabilities, watching it glide smoothly across the workshop, landing gently and precisely, convinced even skeptics that controlled human flight was theoretically possible. This model also served as my reference point for understanding what human flight would actually require. The pilot would need to launch from significant altitude, a high cliff or tower, and possess considerable skill in reading air conditions and controlling the machine through weight shifts and control surface adjustments. Weather conditions would be crucial, with successful flights possible only in steady, favorable winds. Most importantly, the model demonstrated that human flight would be an intensely active endeavor requiring constant attention and skill. Unlike the sycamore seed that flew itself through built-in stability, a human flying machine would require continuous piloting. The human would be both passenger and control system, responsible for maintaining stable flight through ongoing adjustments and corrections. The success of my wooden gliding model represented the culmination of decades of study and experimentation. It proved that the principles I had discovered through observing birds, dissecting specimens, studying airflow, and analyzing natural flying seeds could be successfully applied to human-scale machines. Flight was not magic or divine mystery, but engineering, and engineering problems could be solved through patient investigation and intelligent design. Yet even as I celebrated this achievement, I recognized its limitations. I had solved the theoretical problem of human flight, but not the practical one. Building full-scale flying machines would require resources, materials, and testing conditions beyond what I could access in Milan. More challenging still, successful flight would demand pilots willing to risk their lives testing unproven machines from dangerous heights. My wooden flying model had shown me both the possibility and the difficulty of human flight. It would fly, but flying it would require courage, skill, and conditions that might rarely align. Still, it represented proof that the dream I had pursued since childhood was not impossible, merely waiting for the right combination of knowledge, materials, and human determination. The success of my gliding models had filled me with such optimism that I began designing elaborate machines for human flight, convinced that the remaining challenges were merely matters of engineering refinement. I spent months creating detailed drawings of ornithopters flapping wing machines that would allow humans to fly like birds through the power of their own muscles. My designs were intricate and beautiful. I drew mechanisms that would convert the motion of human arms and legs into the complex wing movements I had observed in birds. Pulleys and levers would amplify human strength, allowing a pilot to generate the rapid, powerful wing beats necessary for flight. The pilot would lie within a wooden frame, strapped into a harness that connected to an elaborate system of ropes, gears, and articulated wings. I was particularly proud of one design that incorporated everything I had learned about wing anatomy and airflow. The artificial wings featured jointed sections that could bend and twist like bird wings, with individual feathers made from carved wood and stretched cloth. The pilot could control not just the up and down motion of the wings, but also their shape and angle, mimicking the sophisticated control that birds possessed. I constructed a full-scale prototype of this machine in my workshop, a magnificent contraption that filled nearly the entire space. The wings spanned more than 30 feet, covered in carefully tailored cloth that replicated the smooth surface I had observed on bird wings. The mechanical systems were marvels of precision engineering, with bronze bearings and carefully balanced levers that multiplied the pilot's strength. But when I strapped myself into this machine and attempted to operate it, reality destroyed my optimism completely. Despite my best efforts, despite the mechanical advantage built into the design, I could barely move the massive wings through a single complete stroke. The force required was enormous, far beyond what human muscles could sustain even for a few seconds, let alone the continuous effort that flight would require. I had made a fundamental error in my calculations, an error that became painfully obvious once I attempted practical testing. I had focused so intently on replicating the mechanical aspects of bird flight that I had failed to properly account for the strength-to-weight relationship that made such flight possible. A sparrow weighs perhaps half an ounce, but possesses flight muscles that comprise nearly a quarter of its total body weight. These muscles are not just proportionally large, but also fundamentally different from human muscles, capable of contracting at tremendous speeds with extraordinary power output. Scaling this capability up to human size created an impossible situation. For a man to achieve flapping flight using bird-like wing mechanics, he would need flight muscles weighing more than 40 pounds and consuming energy at rates that would exhaust him within minutes. The wings themselves would need to be correspondingly massive to provide sufficient lift, adding even more weight that would demand even larger muscles, creating a spiral of impossibility. I spent days performing calculations, trying to find some combination of wing size, muscle power, and mechanical advantage that would make human-powered flapping flight feasible. Every approach led to the same conclusion: humans were simply not built for this type of flight. Our muscle distribution, our skeletal structure, our entire physiology was optimized for walking and manipulation, not for aerial locomotion. This realization forced me to examine my mechanical wing harness not as a flying machine but as a monument to misunderstanding. Every elaborate mechanism I had devised was based on the false assumption that human flight should mimic bird flight in its methods rather than just its results. I had been trying to turn humans into birds rather than designing machines suited to human capabilities. The harness became a powerful teacher through its failure. It showed me viscerally what my anatomical studies had revealed intellectually, that successful flight required solutions matched to the capabilities of the flyer. Birds could power flapping flight because they were built for it. Humans would need different solutions because we were built differently. This understanding led me away from complex mechanical systems towards simpler approaches. If humans lacked the power for flapping flight, perhaps we could achieve flight through gliding, using our intelligence and skill to work with air currents rather than overpowering them through brute force. I began sketching designs for pure gliding machines, flying wings that would carry a human pilot without requiring any power input beyond the initial launch. These designs were dramatically simpler than my ornithopter, consisting essentially of carefully shaped wings with minimal control systems and a secure position for the pilot. But even these simpler designs revealed the magnitude of the challenge. To provide sufficient lift for a human at reasonable gliding speeds, the wings needed to be enormous. My calculations suggested a minimum wingspan of 25 feet for a machine that could carry a man of average weight. Such a machine would be extremely difficult to transport, launch, and control. More troubling still was the question of how a pilot would learn to fly such a machine. Birds learn flight gradually, starting with short hops and building their skills over months of practice. A human pilot attempting to fly a full-scale gliding machine would have no opportunity for gradual learning. The first flight would also be the first test of both machine and pilot, with potentially fatal consequences for failure. I constructed scale models of my gliding designs and tested them extensively, but the gap between model performance and human scale requirements remained daunting. The models flew beautifully in favorable conditions, but were easily upset by minor air disturbances. A human pilot would need exceptional skill and favorable conditions to achieve safe flight. The mechanical wing harness taught me another crucial lesson: that complex machines were not necessarily better machines. The elaborate mechanisms I had devised to replicate bird wing motion were not just impractical but counterproductive. They added weight, created points of failure, and required maintenance that would be impossible during flight. The most successful flying machines would likely be the simplest ones that achieved their purpose. This principle extended beyond mechanical simplicity to conceptual simplicity. Instead of trying to replicate every aspect of bird flight, Successful human flight machines should focus on achieving controlled gliding through the most direct means possible. Elegance lay not in complexity, but in finding the minimum necessary elements for safe, controllable flight. As I dismantled the wing harness and stored its components, I felt both disappointment and liberation. Disappointment because I was abandoning designs that had consumed months of work and represented my most sophisticated engineering efforts. Liberation because I was free to pursue approaches better matched to human capabilities and practical constraints. The failed harness remained in my workshop as a reminder of the importance of understanding limitations as well as possibilities. It had taught me that engineering was not just about what could be built, but about what should be built, given the constraints of materials, power, and human capability. My focus shifted entirely toward gliding flight, toward machines that would work with human limitations rather than requiring superhuman capabilities. These simpler machines would demand different skills from their pilots, not the raw power needed for flapping flight, but the intelligence and sensitivity needed to read air conditions and maintain control through subtle adjustments. The path to human flight, I now understood, lay not in becoming more like birds, but in becoming better at being human using our intelligence, our ability to build tools, and our capacity for learning to achieve flight through methods that matched our nature rather than fighting against it. The failure of my elaborate wing harness had stripped away my misconceptions about flight, leaving me with a clearer understanding of the fundamental forces at work. But it was during my investigations of water flow that I discovered the deeper principle that explained not just how birds flew, but why the curved wing shape was so crucial to their success. I had always known that water and air behaved similarly, but it was while observing the flow of water over the curved hull of a boat that I made the connection that would transform my understanding completely. Standing on a bridge over the Naviglio Canal, I watched the water divide as it met the bow of a passing vessel. The water moved faster along the curved upper surface of the hull than it did along the flatter bottom, creating visible differences in the water's behavior. This observation sparked an insight that sent me rushing back to my workshop. If water moved at different speeds over curved surfaces, then air must behave the same way. And if air moved at different speeds above and below a bird's wing, that difference in speed must be the source of the lift that kept birds aloft. I immediately began testing this hypothesis with my most sensitive instruments. I created thin wooden vanes that could detect even slight air movements and positioned them above and below curved surfaces in moving air streams. The results confirmed my theory perfectly. Air moved faster over the curved upper surface of wing-shaped objects than it moved beneath the flatter lower surface. But understanding that air moved at different speeds was only half the discovery. The crucial question was, why did this difference in airspeed create an upward force? The answer came through careful observation of what happened when air moved at different velocities. I filled a series of glass tubes with water and connected them to curved surfaces in air streams. When air moved over these surfaces, the water levels in the tubes changed, rising on one side and falling on the other. Faster moving air created lower pressure, while slower moving air maintained higher pressure. The curved wing shape was creating a pressure difference between its upper and lower surfaces, and this pressure difference generated the upward force that supported birds in flight. This discovery revolutionized my understanding of everything I had observed about flight. The soaring hawk that remained motionless in a steady wind was not defying gravity through mysterious means. It was positioned in an airstream that moved over its curved wings at precisely the right speed to create lift equal to the bird's weight. The effortless gliding I had witnessed was the result of birds maintaining the forward speed necessary to keep air flowing over their wings at lift-producing velocities. I documented this principle meticulously in my notebooks, creating detailed drawings that showed how air flowed around wing shapes and where the pressure differences developed. These drawings became some of my most important scientific work, capturing in visual form a principle that would not be fully understood by natural philosophers for centuries to come. The pressure principle explained mysteries that had puzzled me for decades. Why were bird wings curved on top and flatter on the bottom? because this asymmetrical shape created the maximum difference in airflow speeds and therefore the greatest pressure differential. Why did wings need to meet the air at a slight upward angle? Because this angle of attack optimized the airflow pattern and enhanced the pressure difference. Most importantly, the principle explained why flapping was not the primary source of lift in bird flight. The up and down motion of the wings served mainly to maintain forward speed through the air, ensuring that air continued flowing over the wing surfaces at the velocities necessary for lift generation. The actual lifting force came from the continuous passage of air over the curved wing surfaces, not from the wings pushing downward against the air. This understanding transformed my approach to designing human flying machines. Instead of trying to replicate the complex flapping motions of birds, I could focus on creating fixed wings with the optimal curves and proportions to generate maximum lift from airflow. The challenge was not to power continuous wing beats, but to achieve and maintain the forward speed necessary for effective lift generation. I began testing wing shapes systematically, creating dozens of small curved surfaces and measuring their lift generating capabilities in controlled airstreams. I discovered that slight modifications in curve shape could dramatically affect performance. Wings that were too flat generated insufficient lift. Wings that were too curved created excessive drag. The optimal wing shape required precise balancing of multiple factors. These experiments revealed that the most effective wings were not simple curves but complex shapes that varied their curvature along their length. Bird wings were thickest and most curved near their attachment to the body, gradually becoming thinner and flatter toward their tips. This variation in curvature optimized airflow patterns and lift distribution across the entire wing surface. The principle of pressure differential also explained phenomena I had observed in other contexts. Sails on ships worked through similar mechanisms, creating pressure differences that propelled vessels forward through water. The curved surfaces of architectural arches distributed weight through pressure principles similar to those governing flight. Even the flow of water through curved channels followed the same fundamental laws. This universality gave me confidence that I had discovered something fundamental about the nature of moving fluids, whether air or water. The principle was not limited to flight, but applied wherever curved surfaces interacted with flowing media. This knowledge could be used not just for flying machines, but for improving ship design, architecture, and engineering in general. I created a special notebook page documenting this principle with my clearest drawings and most precise explanations. This page became my most treasured scientific achievement, capturing in visual form the secret that nature had embedded in every bird wing, every fish fin, every sail that had ever caught the wind. The notebook page showed cross-sections of wing shapes with arrows indicating airflow velocities and pressure levels. I drew the curved paths that air followed as it divided around wing surfaces, reuniting downstream in smooth, efficient patterns. Most importantly, I illustrated how the pressure differences created by these airflow patterns generated the upward forces that made flight possible. But documenting the principle was not the same as applying it successfully to human flight. Understanding why birds could fly with such apparent ease only highlighted how challenging it would be to create human-scale machines that could achieve similar performance. The precision required in wing shape, the speeds necessary for adequate lift generation, and the control systems needed for stable flight all presented formidable engineering challenges. Yet this deeper understanding also provided hope. If flight was based on discoverable physical principles rather than mysterious forces, then human flight was not impossible, but merely difficult. The right combination of materials, design, and skill could potentially create flying machines that worked as effectively as bird wings, even if they worked through different mechanisms. The principle, pressure differential, became the foundation for all my subsequent flight investigations. Every design decision, every test, every modification was guided by understanding how changes would affect airflow patterns and pressure differences. I had moved beyond simply copying what I observed in nature to understanding why nature's solutions work so well. This knowledge also made me realize how mistaken the common understanding of flight truly was. Most people watching birds saw only the obvious flapping motion and assumed this was the source of flight. They missed the invisible but crucial interaction between curved wing surfaces and flowing air that actually generated lift. The flapping was merely the mechanism for maintaining the airflow necessary for lift generation. My notebook page documenting the pressure principle represented the culmination of decades of investigation into the mystery of flight. It showed that the secret lay not in magic or divine intervention, but in the elegant physics of curved surfaces interacting with flowing air. Birds were not defying natural law, but exemplifying it, demonstrating principles that humans could learn, understand, and eventually apply to achieve their own mastery of the sky. As I sit in my final workshop in France, surrounded by the artifacts of a lifetime spent pursuing flight, I find myself reflecting not on what I failed to achieve, but on what I came to understand. The sketches and models that fill this room represent more than failed attempts at human flight. They document a journey from misconception to comprehension, from assumption to knowledge. The final flying machine sketch that lies before me on my work table embodies everything I learned during decades of investigation. Gone are the elaborate flapping mechanisms and complex mechanical systems of my earlier designs. This drawing shows elegant simplicity, a human pilot lying prone within a lightweight frame, beneath fixed wings shaped according to the principles I discovered through countless observations and experiments. The wings in this final design feature the precise curve I learned was necessary for optimal lift generation. They are not too flat, which would provide insufficient lift, nor too curved, which would create excessive drag. The proportions reflect my calculations of the minimum wing area needed to support human weight at achievable gliding speeds. Every element serves a specific aerodynamic purpose, with no unnecessary complexity to add weight or create mechanical failure points. Looking at this drawing, I know it would work. A skilled pilot, launched from sufficient height under favorable conditions, could achieve controlled flight with this machine. It incorporates all the principles I discovered: the pressure differential created by air flowing over curved surfaces, the importance of maintaining forward speed for continuous lift generation, the need for inherent stability through intelligent design. Yet I also know why I never built and tested this final design. It would require not just the machine, but also the courage to trust one's life to untested principles, the skill to control a gliding machine through weight shifts and subtle movements, and most critically, the perfect conditions that would allow safe flight and landing. The gap between theoretical possibility and practical achievement remained formidable. This gap taught me something profound about the nature of human progress. Understanding a principle is not the same as implementing it successfully. Knowledge must be combined with material, skills, courage, and favorable circumstances before it becomes achievement. My investigations had bridged the gap between mystery and comprehension, but others would need to bridge the gap between comprehension and accomplishment. The common misconception about flight that had puzzled me since childhood, that flapping wings were the source of lift, persists because it represents what people see rather than what actually occurs. When someone watches a bird fly, the wing movement is obvious and dramatic. The invisible interaction between wing shape and airflow that actually creates lift cannot be seen without careful study and proper understanding. This blindness to underlying mechanisms extends far beyond flight. In every field of human endeavor, people mistake the visible for the essential, the obvious for the important. They see the flapping and miss the physics. They focus on symptoms rather than causes, on appearances rather than principles. My study of flight taught me to look deeper, to question assumptions, to seek the mechanisms that underlie observable phenomena. This approach proved valuable not just for understanding how birds fly, but for investigating architecture, anatomy, engineering, and natural philosophy in general. The habit of careful observation combined with systematic investigation became my method for approaching any mystery. The artifacts scattered around my workshop tell the story of this investigation. The childhood kite of linen scraps represents wonder and curiosity. The preserved crow wing demonstrates the importance of understanding structure before attempting function. The glass sphere that revealed air currents shows how invisible forces can be made visible through intelligent experimentation. The sycamore seed that taught me about rotational lift sits in its place of honor, a reminder that nature's most elegant solutions are often hidden in plain sight. The wooden gliding model that proved my theories correct represents the moment when understanding translated into practical demonstration. Even the failed wing harness serves as a valuable reminder about the importance of matching solutions to capabilities rather than forcing inappropriate approaches. Each artifact contributed to my growing understanding that flight was not about conquering natural forces, but about collaborating with them intelligently. Birds succeeded not by fighting gravity and air resistance, but by using these forces as partners in achieving controlled motion through three-dimensional space. This principle of collaboration with natural forces, rather than domination of them, became central to my approach to all engineering challenges. The most successful machines, I learned, were those that worked with the properties of materials and the laws of physics rather than trying to overcome them through brute force or excessive complexity. My final flying machine design embodies this philosophy completely. It does not try to replicate bird flight through mechanical complexity. Instead, it applies the principles that make bird flight possible to a machine suited to human capabilities and limitations. It represents collaboration between human intelligence and natural law. But perhaps the most important legacy of my flight investigations is not any particular design or discovery, but the demonstration that careful observation and systematic investigation can reveal the mechanisms underlying apparently mysterious phenomena. Flight seemed magical to most people in my time because they did not understand the physics involved. Once these physics became clear through proper study, flight was revealed as challenging engineering rather than impossible magic. This transformation from mystery to engineering problem represents the proper relationship between human intelligence and natural phenomena. We need not accept mysteries as permanently inexplicable. Through patient investigation, careful experimentation, and honest acknowledgement of what we observe, we can understand even the most complex natural processes. The knowledge I gained about flight will outlast the specific machines I designed. Future investigators, with better materials and more advanced understanding, will build upon the principles I discovered. They will create flying machines that achieve what my designs only approached. My contribution was not to solve human flight completely, but to establish it as a soluble problem. I leave behind drawings, notes, and artifacts that document not just what I discovered, but how I discovered it. The methods of investigation are as important as the results. Future students of flight will need to conduct their own observations, perform their own experiments, and reach their own understanding. But they will not need to start from the misconceptions that delayed my own progress for so many years. The greatest misconception about flight that it comes from flapping rather than from the interaction between wing shape and airflow has been documented and explained. The invisible forces that create lift have been made visible through proper investigation. The principles that govern successful flight have been identified and recorded. What remains is for others to apply this knowledge with the courage, skill, and favorable circumstances that I could not command. They will succeed where I could only point the way. They will fly where I could only understand flying. But understanding was my purpose, and in that I succeeded completely. The mystery that had fascinated me since childhood was revealed not as magic, but as physics. The birds that had seemed to possess supernatural powers were shown to be sophisticated applications of natural law. The sky that had appeared forever closed to human access was proved to be governed by discoverable principles that human intelligence could comprehend and eventually exploit. This knowledge is my legacy, that flight is possible, that it follows understandable rules, and that those rules can be learned by anyone willing to observe carefully and think systematically about what they see.